this video, I'm going to be going through questions from Engineering Mechanics by Auni El-Haj, the guy who does the Eureka Engineering videos. So I'm doing questions on bending moments and bending moment diagrams, that sort of stuff. And we're going to be mostly focusing on question 50 and on page 50 on. But before we get there, there's question 19, draws a shear force diagram that looks like this. And it asks, at which of these points, A, B, C, D, or E, where is the maximum bending moment diagram? Where is the maximum bending moment likely to be? So, what we know is if this is the shear force diagram, the bending moment diagram, well, is going to be the area of each of these blocks. Okay, so if I have this as block 1, the answer is going to be C. Right? And I can tell it's going to be C because that's where it crosses the x-axis. But let's go through it and look at that. Okay, so I'm going to call this block 1, block 2, block 3, block 4, and block 5. They're the 5 blocks that we're going to add. Okay, so we always start off at 0. We start and end in 0, and it's often not clear with shear force diagrams and bending moment diagrams that we in fact start and end at 0. And the same is true for our bending moment diagram. So we start off at 0. I've talked about how there is no left-hand side. So if there's no left-hand side, the effective, if left hand is equals right hand, if left hand doesn't exist, it has to be 0. But if that doesn't make sense to you, don't worry too much. Just know that we start and end on 0 at the end of the beam. So this first block has some amount of area. We're going to put that amount there. It doesn't matter, we haven't been given values. This next block, actually there's 2 blocks here. But we're just going to treat it as one big block. It's a bit of a mistake, but we're going to do that. It's a big area in that second block. There's actually 2 parts to it, so it's going to be something like that. But I didn't identify it earlier. This next block, it's negative, so we're going to go down, but we're only going to go down a little bit. Then the next block, we're going to go negative again, and more and negative. And then here, actually we're going to be a little bit flatter than that. And then this last block is very negative, so it's going to get us back down to 0. That's what I would predict this bending moment diagram to look like. And what we can see is that our maximum bending moment diagram, sorry, I'm going to shift that just a little bit. It's actually a little low, that's better. And then something like that. There you go. So just to try and get this lined up. The idea is that when you do calculus, you'll learn that maximum values occur when the integral or the derivative, relatively speaking, where we cross the x-axis is where we get our maximum values. And so in the case for shear force diagrams, our maximum bending moment will occur where our shear force diagram is equal to 0. Okay. I would just say that the simple answer is because it crosses the axis, that's where it's going to be, but we just proved it by doing this diagram here. It's hard without values. I just took guesses at things, but we have a rough idea. Moving on, now we're going to get into some serious calculations. So that was sort of our warm-up. And so we're going to question 50 on page 50. And our first, we've got a free body diagram, and it's going to be 3, 6, 3. 3 meters, 6 meters, 3 meters. And the roller is on this side. Remember, in the HSC, there has to always be 1 pin and 1 roller, or it has to be a fixed reaction, so a single fixed cantilever. That's what it says in the syllabus. So we've got 30 and 40 kilonewtons or newtons?
Kilonewtons.
Okay. And we've got 3 meters, 6 meters, 3 meters. Okay, so this is the free body diagram. And now what we need to do is we need to do we need to find the reactions. So which reaction are we going to find first, the pin or the roller? Okay, we want to find Ricky the roller because she's younger and less complicated, right? And we're going to do that by taking moments about the pin. Do these have letters?
No, A and B.
Yeah, this is A, so this is going to be reaction A, or Ra, and this is going to be RB, or red balloon. So what we're going to do is we're going to say clockwise sum of the moments relative to point 0. So we're going to be measuring all of our from point B. All of our points are measured from 0. B equals 0. And so we can say, well, 0 equals, and then starting at, we're going to go left to right. We're going to say, well, we're going to have the reaction at A. Now, as the reaction at A relative to B, if I put my finger on B and spin it, are we going? So see how I'm lifting? If this was a hand of a clock, if I lifted the clock in this way, it's going clockwise or anti-clockwise? Clockwise. So it's going to be plus RA, and how far away is it?
9 meters.
RA, or Ra is 12 meters away. 3 plus 6 plus 3 is 12. Now, I like to write it like that. That's how I do it. I see a lot of students who write it as like RA times like that. I just think that that's unnecessary. Like in maths, we're allowed to just write the number times the fraction. Yeah. To me, that's just the time symbol just makes it. The brackets make a nice time symbol. Okay. The next force is we have 30. Now, is that going relative to B? If this is a hand of a clock.
Anti-clockwise?
Anti-clockwise. So we're going to keep that as minus. And what's the distance away?
6.
Nope.
9.
9. Excellent. Lots of people would just write 6 there. Lots and lots and lots of people. That's why I write the brackets. It helps me to remember that there's two numbers, that often multiple numbers. Okay, the next one is 40 relative to B. This is a clock anti-clockwise, so we're going to keep it, and it's 3 meters away. Okay, so this is our equation. So what we're going to have here is 0 equals 12 Ra minus 3 times 9 is 270 minus 120. Are you okay with this? Do you have a calculator that can do that?
I have a phone, but I'm still waiting.
Let's see if I have a calculator floating around up here.
So that just be 115.
Feel free to skip if you're watching a video. Okay. Anyway, so what we're going to do is we're going to get minus 270 minus 120, so that's going to be the same as 390, is that right?
Wouldn't it be 115?
No, because this is minus minus.
Oh, okay.
Yeah? So what we're going to do is we're going to add both of those to the other side. Right, we're going to add 270 to the other side plus 120 on the other side is going to give us 390, I think. Yeah. Okay, equals 12 RA. I've left out 12 RA. Then what I can do is I can divide both sides by 12. And so I can say that RA equals 390 divided by 12 equals 32.5 kilonewtons up. So that's RA equals 325 kilonewtons up. By the way, you should be able to find the answers in the book if you want to keep checking. So rather than getting the calculator out, you can just follow the working out in the work solutions. Okay, so now we want to find RB. To find RB, I'm going to use a square off a little space here. I'm going to say we're going to use sum of the forces vertically equals 0. Now, I usually draw this as a little diagram rather than working it out mathematically. I will have shown you at some point how to do it the other way, but 30 plus 40, and then I've got 32 going up. So what is the missing amount? The missing amount here is going to be RB. Okay.
Yep, that's right.
70 minus the answer equals 37.5 kilonewtons up. I find that when I write it this way, I'm much less likely to get mistakes. So I'm going to write this as 37.5 equals RB. Now that I've got that, I'm now going to draw my shear force diagram. So I draw a line for 0. I can do it better than that. Give myself a little bit more room too. Okay. Once upon a time there was a shear force diagram. It started at 0 and it went up 32. Dum-de-dum-de-dum. It went across for 3 meters. Then something bad happened. It went down 30. So now it was at 2.5. It went along at 2.5 for quite a long time. But then something scary came along and it went down again, and now it was at minus 37.5. But luckily, at the end, reaction B came along and returned everything back to the way things were at the start. So that's what the shear force diagram looks like. This is a positive area, these ones are negative areas. Now when we looked at how to draw bending moment diagrams earlier, what we can remember is that we're just going to draw a running total of our areas. So this one is 32 times 3 meters. So 32.5 times 3 equals 97. We know our maximum is going to be up here. How do I know that my maximum is going to be at this location?
Because that's where it crosses.
Exactly right. Okay, so then I'm going to add on 2.5 times 6. So I'm going to add 15. So this one here is going to be 97 plus 2.5 times 6. And that's 15. The reason I write plus and plus is because sometimes we get minus areas, and I want to remind myself that there can be minus areas. So 15 plus 97.5. Why 97.5? Because that was the value we had back here. And now we then are going to, we know it's going to be 0, but let's prove that it's going to be 0. So what this area is going to be is 112 or 112.5. This area here, this block, is going to be 112.5 plus minus 37.5 times 3. Okay, if we do 37.5 times 3, we get exactly that number, which brings us back to 0. And that's our bending moment diagram. Now, does this question ask for anything else? It does. It then says it wants us to figure out, oh no it doesn't, that's it, that's all it wants, right? Bending moment diagram, shear force diagram?
Yeah, shear force and bending moment, yeah.
Okay, so if we were to calculate a question that asked for bending stress, the value for m times y over I, the value for m that we would use would be that one, because it's the biggest value on the diagram. So if you're wondering why do we draw these diagrams, we draw these diagrams for a couple of reasons. One, to find the maximum bending moment. Two, to figure out if we need any shear reinforcement. If it's concrete, right, we add stirrups for shear reinforcement. For three, we want to know the direction where we need top steel or bottom steel and how much steel. So we might put more steel in this location compared to there where we just have one bar going, or a smaller number of bars running all the way through, and we'll put more bars in the area where it needs it. Also, we might redesign our loads. We might reposition where things are going to be. We might add another wall to add in another support. Those are the reasons why we use these diagrams. But mainly from a mathematical point of view, we want to find maximum values so that they can go into our bending moment diagram. Our shear force equation. Okay, I'll just clearly label this as a bending moment diagram, and we're ready to move on to question 51. So, okay, question 51. So, you know, we're going to skip question 51, and I'll tell you why. We're going to go to question 52. Yeah. So, question 52. The reason I'm skipping 51 is because it has a uniformly distributed load. And at a university level, right, that is absolutely a question that can come up. In the Australia or the New South Wales syllabus for engineering studies, we cannot give you a question that has uniformly distributed loads. So, well, we will do them, but we're not going to do them now because we want to remember that it's not a question that can be given in the HSC. So what we've got for question 52 is we're given a free body diagram that we have 2 meters, but I don't have the rest of the dimensions. So you're going to have to tell me that. So it's 2 meters, and then it's down 10, 2 meters, then it's up 4.
Then it's 5 meters.
5 meters, yeah, okay.
And then after that it's 1 meter.
Okay. They're kilonewtons, I'm assuming?
Yeah,
Okay, so we're going to find the reactions as well. Which one's the pin, which one's the roller?
They didn't show.
They don't show? Okay, now we talked before about finding the pin versus the roller. It doesn't really matter if there's no horizontal forces. So just as a convention, we like to find the pin first by taking moments, we like to take the roller first by taking moments about the pin. But if there's no horizontal component, it doesn't really matter. This here, we have a force that is extended out beyond the reaction, right? So because we have a force that's extended past the reaction, that means this is a cantilever. Copeland has said that he is a big fan of cantilever questions. So, you know, he doesn't write the exams, but he is definitely influential. So, to keep that in mind. Okay, so what we're going to do first is, do we want to find the left or the right reaction? I don't care, you pick. Do we want to find this one or that one? Do they label these with letters?
A?
So A?
Yeah.
Okay, so this is Ra. We're going to find Ra or we're going to find red balloons?
Both.
Okay, we're going to start by finding Ra. Okay, to do that we're going to take moments about RB, yeah? Okay, so what we're going to do is we're going to say this clockwise, we're taking clockwise as positive as our convention. We're taking the sum of all moments measured from any point equals 0, but we're going to try and find A, our unknown, by measuring from point B. So we have two unknowns. We can eliminate this unknown by multiplying it by 0. If we multiply it by 0, it doesn't matter what it is, and that will allow us to find RA. Okay, so that's why we're measuring everything from point B, and so we can eliminate A. So what we're going to say is 0 equals, now in this case, if we take moments about, it's going to be pretty similar to the last one, but RA, is it going clockwise or anti-clockwise?
Clockwise?
Clockwise. So plus RA multiplied by what distance?
4, 5, 10.
No, it's 9. 2,
Oh.
2, 5. We don't count that one because we're
Is it
measuring
past
from point there. Yeah, that's exactly right. But that's good. I'm glad that you got that. I'm glad we learned that. So this one here, 10, is it going clockwise or anti-clockwise?
Anti-clockwise?
Okay, and its distance is 2 plus 5 is 7. And then the next one we have is 4. Is that going clockwise or anti-clockwise?
Clockwise.
Clockwise. Multiplied by 5. And then RB. Now normally I'd write RB equals 0. So, well, I just write here RB plus 0 because it's 0 distance away. And then here I'd have, so this last one, 1 meter, is it going clockwise or anti-clockwise? So relative to B, if B is the center of my axle, or the center of my clock, and this hand is being pushed down, in this direction is it going clockwise or anti-clockwise?
And
Anti-clockwise. Wait.
the clock.
Yeah, you got there. Okay, clockwise. Yeah, that's where a clock turns. 5, and it's by 1. Okay, so what we're going to get here is we're going to say 0 equals 9 Ra minus 70 plus 4 times 5 is 20. Yeah, that's right. Plus 0 plus 5. Okay, so what we're going to get here is we're going to say 0 equals 9 Ra minus 70 plus 20 plus 5 equals minus 45. I want to get this minus 45 over to this side, so I'm going to add 45 to both sides. So that means we're going to say 9RA equals 45, and we can then simplify that to say RA equals 45 divided by 9, which is 5. Okay, now we made some assumptions. In other videos, I've gone into a lot of detail with reactions. We talked about how we made an assumption here. We assumed that it was going up. Right? I think they drew it as an arrow. So if it's going up, it's therefore clockwise. If it's going up, it's clockwise. And then so we can say here that our answer is positive. Therefore, our assumption was okay. Right? Rather than NG for no good. Our assumption was okay. Therefore, it's up. Yeah? You don't need to write that, I just write that. The same as you don't need to write that, you don't need to write that. I write that just to be clear. right? So for the sake of transparency. Okay. Now, if we wanted to, we could just as easily have found RB by taking moments from the other side. I don't know if I have the enthusiasm to do that right now, and it's just a lot faster to do some of the moments, some of the forces. So what I'm going to say now is sum of the forces vertically equals 0, and so I know that if I have 10 going down, and 4 going down, and 5 going down, and then going up I have 5 going up, well, how much is missing? I just want to check. 1, 2, okay. That's whoopsie daisy. Okay, so what have I got? Let's go through it again. I have RA is 5 going up. 5 going up. If I go through, I have 10 going down. I have another 4 going up. I have another 5 going down. And then I have RB in the middle here, which is some number that I'm not sure. Now, I haven't drawn these exactly to scale. I'm going to draw this a little bit better. 10 and 5. What is the missing amount here? Well, this side is 15 and this side here is 9, so it means I need 6 for it to work, yeah? Does that make sense?
5 minus 9. Yeah.
Okay, so that means that we've already found RA, so this one's going to be RB. RB equals 6 kilonewtons up. So I'm going to write these in here. Equals 5. Now, you're just checking with the back of the book, right, for all these answers? Okay, so now we're going to go to the shear force diagram, and we're going to tell, once upon a time there was a beam, and that beam started at 0, and then it went up 5. It went across for 2 meters, and nothing happened for a while, until suddenly a big scary force of 10 newtons came along and went down 5. But it was a bit of a roller coaster, because then, in the darkness, the beam found a friend who helped it by going up 4 kilonewtons. We went across again for another 5 meters, and then things were looking really good, and they went up 6, but then at the end, everything went back to normal, because it was a bit of a downer at the end. Okay, so that's our beam. I want to write this area, so we're going to call this block 1, which is positive, block 2, which is negative, block 3, which is also negative, and block 4, which is positive. So, what is our bending moment diagram going to look like? What a lot of people like to do is they like to imagine, how is this beam going to bend? And so, well, if you've got this pushing up and this pushing up, you're going to have something that goes down, then up a little bit, and then like that. That's probably what it's going to look like, something along those lines. Because we've got this 4 pushing up here, then you have more pushing it up later. So it's going to probably push up even a little bit higher, a little bit steeper like that. Something along those lines. Smoothing this out. Something along those lines. Now, some people draw their bending moment diagrams in that direction, but we can predict that our bending moment diagram, because it's not going to have any curves, because there's no uniformly distributed loads on this beam, it means that it's going to look something I would predict like this. I would predict it's going to look something in that ballpark. I don't know where that horizontal line is going to be. It might be steeper, it might be lower, but I'm going to predict it's going to look something like that. Let's have a look at what the answer looks like.
The answer at this bookmark.
Okay. I'm going to sit just so I can access more board. Okay, so once upon a time, there was a bending moment diagram that had 0. The first block had an area of 10, right? 5 times 2 equals 10. And so that's going to be this value here, 10. We predict that our maximum values are going to be here and here. When we talk about maximum, remember we talk about absolute values? We have maximums and minimums, but our positions do line up. So I should draw that a little bit better. Something like that. So our things line up. Okay, then, so this is 5 times 2 equals 10 kilonewton meters. then we're going to have a minus. We're going to have, what is this area here below the line? It's 5 kilonewtons times 2 meters. Oh, that gets us straight back down to 0. Okay, so my diagram's already, my estimate is a little bit wrong. Let's see how wrong it is. Then we go back to here, we're 1 kilonewton below the line, and we're multiplying by 5 meters, which means that we're going to go down negative 5 kilonewton meters. So we're back to 0, so we've got 10 minus, or plus brackets, minus 5 times 2. And then here we've got 0 plus brackets minus 1 times 5 equals minus 5 kilonewton meters. And then we're going to go up at the end, we're going to go 5 times 1. And 5 times 1 brings us back to 0. So my diagram, it was close. Wasn't perfect, but it was close. And this is where thinking about what it should look like gives us an idea. Is that what the book says?
Yeah, it's just more of a triangle, kind of.
Yeah, I can live that. Okay, so now what we were asked to do in this question is we're asked to find the shear force, or maximum bending stress is what we're going to find. Okay, so what is our maximum bending moment in this diagram? Well, even if we take absolute values into account, the maximum here is 10 or minus 5. We'd rather design for 10 kilonewton meters, positive or negative, especially if it's a steel beam, we'd rather deal with that. If it was concrete, it would be slightly different. If it was concrete, we would design the steel that needs to be here would be a little bit more there, a little bit more steel in that location, and then we'd need some amount of steel on the top, putting more steel, a little bit more steel there. That's how we would design it, and we'd design this for that value. But for steel, because it's equally strong top in tension or compression, we just use the biggest value, the absolute value that is the largest. Sorry?
It says determine the maximum bending stress on the beam at the second moment of
area. Yeah, I've got the second moment of area. Okay, so what we're going to do now is we're going to find the second moment of area. I'm going to say we don't need this anymore, so I'm going to remove this so I don't have to sit in the chair. So we've got our formula for bending stress is sigma b equals m for maximum bending moment times y, which is the distance from the neutral axis to the extreme fibre, divided by I. So let's have a look at our values here. So I'm going to write here over here, I'm going to write data. And data, we're going to say that m we're taking is equal to 10 kilonewton meters, which is equal to 10 times 10 to the 6 Newton millimeters, because we'd rather use Newton millimeters because we use grease units. We go together like megapascals and millimeters squared. Why? Well, okay, to find out why, what we need to know is we need to know the properties of this material. So the properties of this material, we've told that it's 60 and 280. Because it's rectangular, we can assume that the neutral axis, quite reasonably, we can assume that the neutral axis is going to be going through the middle, which means that y, it doesn't matter if we use y to the compression or y to the tension, it's going to be the same, it's going to be 140. But if in doubt, we typically are going to use the larger value, right? Big Y is critical. So Y is going to equal 140 millimeters. And then the second moment of area, or I, the second moment of area is given as 120 times 10 to the 6 millimeters to the power of 4. Is that correct? You're just checking the types and right things in the book? Okay. Sigma b equals 10 times 10 to the 6 times 140, all divided by 120 times 10 to the 6. So what I can do now is I can cross that out and cross that out, and I can say these are probably pretty close. So my answer is probably going to be about like 12 megapascals or something like that. Let's see what our answer is. The reason why I'm making an estimate is a good way to see, are we just totally off? Like, are we ridiculous? Okay, so what we've got is 10 times 140 divided by 120 equals 11.67, and that's going to be megapascals. Okay, that was pretty close to my estimate. And 11.6 megapascals, I would consider that's a very low bending stress, right? Generally, we want to design things close to the strength of the material. Assuming the material is steel, we would probably expect it to be 300. If it's concrete, it's probably not too bad. For concrete, once we apply a factor of safety, it's probably about half what the concrete is allowed for. It's just if it's concrete, we've got to really be paying attention to where we put steel in. That's a little bit beyond the HSC course, but I say that because there have been questions that have asked about those sorts of concepts. Okay, so that's 52. We're not going to do 53 because it's got uniformly distributed loads. We're not going to do 54 because it's got uniformly distributed loads, which takes us up to question 55. Okay, question 55, we're just simply given a beam, and we're told that this beam is, well, it's actually square.
No, it's a beam.
It's a beam? It's rectangular?
Yes.
It doesn't say 200 by 200?
Beam.
Does it not say it's 200 by 200?
Yeah, but it's, yeah, sure.
Okay, great. And then we're told that the second moment of area, what we at university we call an IXX, or in practice we'd call IXX, is 200 times 10 to the 6 millimeters, I should write that as a little m, millimeters to the power of 4. And then we have a maximum bending moment of 76 kilonewton meters, which we're going to rewrite as 76 times 10 to the 6 Newton millimeters, which again is what I would do in practice. Okay, so this question I think is relatively easy. It's easier than the last question. What we need to know is where is our neutral axis. So for this beam, what distance would we say is the neutral axis from the top? It's rectangular, right? So it's going to be symmetrical. So that means the distance y from the NA. So the neutral axis, in case you don't remember that, the neutral axis is the point where it's neither in tension nor compression. If we put this beam in bending, it's going to be squashed at the top, so compression. It's going to be stretched at the bottom. And then there's going to be a line that runs through there that is neither in tension or compression, which we call the neutral axis. It's like Switzerland, right? It's neither compression nor tension. The neutral axis has a distance, so that if we tell this molecule is under, that molecule of steel or whatever, is under maximum compression. It's the most compressed. This molecule here is maximally under maximum tension. Somewhere in between that, there's an area where there's no stress happening at all, the neutral axis. What we're interested in is the distance from the extreme fibre to the neutral axis. We call that, this one here would be YC, and this one here would be YT. And if they're not, in the case of symmetrical beams, they're the same, so we don't care, right? In this case here, we can say YC equals YT. In uni, we'd write a bar on the top, but so therefore we can just say that Y equals D on 2. Y equals D on 2. We just, if there is a difference, we use big Y typically for our critical design, unless they're asking us to find the compression or the tension, which is what they did in one HSC question, which I didn't think was a very good question. So what we're going to say is that Y equals 100 millimeters. We okay with how we got to Y? Okay. Now that we know that, it's fairly easy just to plug some numbers into the formula. Okay, sigma B equals my over I. My over I. Which we're going to say that we've got 76 times 10 to the 6 times 100 divided by 200 times 10 to the 6. Okay, so those cross out. So these zeros cross out. So it's effectively 76 divided by 2 is going to equal 38 or something like that. 76, I did 76 divided by 2. 76 divided by 2 equals 38. And what's the value? Stresses are measured in? Dun, 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 dun. In this case, they're measured in megapascals, not just regular pascals. The reason for that is because We go together like megapascals and millimeters squared. We've chosen to use millimeters for all of our values, and we've converted our meters into millimeters. We've said that there is 1,000, if you said where did this 6 come from, there's 1,000, which is 10 to the 3 newtons in a kilonewton, and there is 1,000 millimeters in a ruler, in a meter ruler, right? So you add those together, that gives you 10 to the 6. Yeah. Okay. 56 doesn't have any bending moment diagrams, so any UDL, so we're going to do 56 as well, and that'll be the last one for this recording. Depending on how keen I am, I may do the UDLs as a bonus video for people who just like learning things beyond the syllabus. Okay, so question 56, we're given a shear force, a free body diagram, an FBD that looks like this. What is it? They told us the length of the beam is 6 meters. L equals 6 meters. They've told us, okay, this is, there's been questions like this in the HSC before. They've told us the force is unknown. They have told us, I have 5.26 written, what does that mean?
5.
They've told us the beam, or draw us the beam.
The second moment of area I for this beam is 5.26 times 10.
Yeah, okay.
Yeah.
Second moment area equals 5.26 times 10 to the 6 millimeters to the power of 4. The reason why it's millimeters to the power of 4, the idea is that you're taking an area, and then you're taking the moment of the area. Instead of a moment force, we're taking a moment of an area, we're multiplying by that, and then we're doing it again. So we're multiplying an area by a distance, and then multiplying by another distance. It's not like some sort of 4-dimensional space-time. Okay, what is 65? That must be the maximum allowable bending stress. Okay, so I wrote down some numbers, I didn't explain what they were to myself. 75 is what we call B, and the depth of the beam is 120, is that right?
Yeah.
D equals 120. Okay, so in that case, our neutral axis, because it's rectangular, is going to be halfway. And so that means that our Y bar for compression and tension are going to be equal. The top is being squashed, the bottom is being stretched. So we can say that Y equals 120 divided by 2 equals 60 millimeters. Okay, this is a good question though. And they've told us that the loading condition looks like this. They've told us that it's a simply supported beam, which means that we can't really draw a diagram, but we could. So first of all, I want to point out that we are allowed just to use this formula. We're allowed to say that for a simply supported beam that's symmetrical with a single load, we can say that M max equals FL on 4. We're allowed to do that. And we could rewrite that formula, but let's prove that first. So what it means is that our shear force diagram is going to look like this. So if this is F, that means our reaction here is going to be half of F, and this here is going to be half of F. So that means that this is going to be F, half of F up, half of F up. Now, what is the area of this block? Well, it's going to be L, half of L, which is going to be L2. L2 is that distance. So that means that this area, the block of this area, is going to be F divided by 2 times L divided by 2, which is the same as saying FL on 4. Are you okay with that? If you don't remember that formula, this is how I would approach it. Yeah? So there are going to be students who are going to look at the question like this and they're just going to blank. They're just going to say, I just can't do it. Doesn't work. Okay. So what we're going to look at now is, with this information that we have, I'm going to rub out the diagram, which is a shame for people who... You still copying it?
Just
I'll work over here. You can see that well enough?
Oh yeah.
Yeah, okay. So what we're going to do is we're going to say that if we know that m equals FL14, m equals FL14, we've found that now twice, we can then say, well, let's multiply both sides by 4, so we get 4m equals FL, which if we divide that means we're going to get 4m divided by L equals F. So let's use that over here. We can say 4m divided by L equals F. Now what we want to do is we want to substitute m. So to substitute m, what we need to do is we need another set of formulas. We need to know that our bending stress equals my over I. What we need to do is we need to rewrite this in terms of I. In terms of n. So what we're going to say is the second moment of area times the bending stress equals m divided by y. We can divide both sides by y. So we can say that m equals I divided by y. So in this place here, we can say 4 brackets I times sigma b divided by y all over L. Which in this case, we've told us L is 6 equals 4. It equals F. Okay, so what is F going to be equal to? Well, we're just going to start multiplying these numbers in. F equals 4 brackets. The reason for the sudden cut is I think that I have a different answer to the book. So we're just going to check my working out compared to the book's answer. I think they've made an order of magnitude error. I will talk about what that would mean for marking. So I am going to use millimeters for L. Typically, I am happy to use meters and then get kilonewton meters and then convert kilonewton meters into my answer. But in this case here, we want to be really, really, really sure that we're doing everything right. We want to be really, really sure that we're giving everything that we're using grease units for everything. So let's have a look at what we're going to have. Now, I am approaching this answer very differently to the book. I think there's something worthwhile to look at how Alni solves that problem. But in this case here, what I'm going to follow my method that I've worked out, and we're going to say that 4 times brackets. Now the I is 5.26 times 10 to the 6, which I must say I'm a little bit tempted often to just leave out. Times 65, all of that divided by 60. All of that then divided by 6 equals our F. So, and that's going to give us, not 60, divided by, because L is 6,000. Yeah, we're doing everything in millimeters. So what we could do, to simplify this a little bit earlier, was we could probably cross out that and put it to cross out those 3 zeros and cross things out. But I'm happy to have a big number if it means that we're going to get the answer right. So I'm just grabbing my calculator. Okay, so I'm going to do this area up the top here. So I've got 526 times 10 to the 6 multiplied by 65 divided by 60. That gives me an answer with some decimal places. I get 4 brackets 5.69 times 10 to the 6. And then all divided by 6,000. Okay, so I multiply that by 4, and then I divide that by 6,000, and I will get an answer. F equals 3799 with rounding. Now, because we've used consistently throughout the whole thing grease units, megapascals and millimeters, right? Because we've used those values everywhere, that means our answer is going to be that number of newtons, which means our answer is going to equal 4.8. It's a terrible 8, so much that it looks a lot like a 6. 8 kilonewtons. I'm pretty confident that's the answer. by all means, I will think about contacting the author and saying that maybe there's a correction already available, but I'm pretty happy that I want to lock that one in. It's possible I'm wrong, in which case, by all means, please let me know how I'm wrong. That will be it for this recording. There are plenty of other questions. We will look maybe at the bending ones with bending moment diagrams, but I want to remind you that we're going to be very careful with those, because the HSC shouldn't give us any questions that require mathematical calculations for things with bending moment diagrams, with uniformly distributed loads.